Hi everyone, I'm Adam Dede and welcome to a Neurojournal Club. So in the last video we talked about how information is represented in consciousness, which parts of the brain represent conscious information, which parts of the brain don't represent conscious information. And just to recap, primary sensory cortices, primary visual cortex in particular, seems not to represent conscious information. But as information flows further up the processing hierarchy and makes it to area V4 and then eventually to the inferior temporal cortex, that information does seem to be conscious. So the next question that we're going to ask is, what determines what gets into consciousness? So it's one thing to say this information is conscious and this information is not, but where was that decided? How did that happen? So let's take a look. So the first thing to realize is that not everything's going to make it in. So we talked last time about the interactions between this area V1, V2, V4, and IT. And you can kind of think about this as a flow of information moving from V1, primary visual cortex, through V2 to V4, and then IT. And that's kind of the canonical way to think about the flow of information moving through the visual system. And the thing is that initially in V1, when you have all of the visual field, every single receptor in your entire retina in both eyes coming into V1, there's just no possible way that you can have all of that information flow meaningfully all the way up to IT. If you happen to be looking at your friend's face takes up a very small area of your total visual field. And that's really the only piece of your visual field while you're having a conversation with that friend that you're actually going to be paying conscious attention to. So what happens to the rest of it, and how is it that that face becomes the stable image held in consciousness? So that's the question we're going to be asking. How does information get selected? So is it selected late? So does information make it all the way up to high areas of cortex, and then these high areas of cortex select which pieces they want? Or do early areas exhibit activity changes? Is it that we have down selection or filtering of information coming into consciousness happening even at really early areas of processing? So the method key idea here is going to be the same as it was in the last video. We're looking again at some studies from Logothetis and colleagues. And this key idea is that you want to compare minimally different situations. So situations where the only difference is stimulus being conscious versus not conscious. And in that way, you can look at consciousness as an actual variable being manipulated in the experiment. So here we're looking at a timeline of what is presented to the monkey. This is a monkey experiment. So at the beginning of the trial, the monkey is just presented with a dot in the middle of the screen, one dot to each eye. And as far as the monkey is concerned, the dot is exactly the same in each eye. So they're just going to be focusing on what to the monkey is a single fixation spot. Then in one of the eyes, a red circle will be presented. And at this point, we can be pretty confident that the monkey is going to have a perception of that red circle. Then, after 1.4 seconds, there's going to be a sudden display of lots of drifting dots all over the place. Now, when these drifting dots come on, there's a possibility that it will induce what's known as global flash suppression. This is a phenomenon whereby lots of sudden movement in the visual field can cause static objects in the visual field to disappear. And in this case, the monkey has been trained to tell us by either pressing or not pressing a lever if he's experiencing the red circle as being currently visible or currently invisible. And in this way, even though the red circle is on the screen physically all the time, we can compare situations where that red circle is consciously visible versus consciously not visible or invisible. Now you may be wondering, can drifting dots really make a red circle disappear? So I prepared a little demo for you to take a look at. Now keep in mind that when different things are presented to the two eyes, it becomes a more rivalrous situation. There's more chance that the red circle will disappear. But in this example, nonetheless, there is a very good chance that the red circle will disappear for you. So what's going to happen is a gray screen will come up. You're going to want to focus on the white plus sign in the middle of the screen. And you'll notice that there is a red circle up and to the left of the plus sign. Even though the red circle is there, keep your gaze focused and fixed on the white plus sign. If you move your eyes at all or if you blink, the phenomenon will be broken. And then a bunch of drifting dots are going to appear on the screen. Keep your gaze focused on the white plus sign, and over time you may see that the red circle disappears. Now, if you think that I'm tricking you and that I've made the red circle disappear, you can always rewind the video and just focus your gaze on the red circle, and you'll find that the red circle stays there for the whole time. So here we go. Go ahead and see how you do. Okay, so now you've understood the idea of global flash suppression. You get the idea that we're trying to compare minimally different conscious and non-conscious perception. What's going on in the brain? So this is what Wilke, Logothetis, and Leopold were taking a look at, what's going on in the brain. And so we're going to look at measurements coming out of area V1, primary visual cortex, V2, and V4. So these first three steps on the processing stream of visual information. So first, let's just take a look at the cell firing. And what we can see is that in V1, primary visual cortex, there's no difference between situations where the monkey says that the red circle is visible versus invisible. So on the left, we're looking at situations where firing decreases. On the right, we're looking at situations where firing increases. But overall, the take-home point here is that there's just not a lot of change. Basically, V1, as we saw before, doesn't care about what consciousness is doing. So now let's go ahead and move up from V1. Let's take a look at that next step, V2. And here again, we can see that really there's not really much difference going on. Now maybe there's a little bit of a difference going on here in this figure on the right, where you can see there's a little bit of an increase in firing rate, but there's not really any significant modulation going on here. V2, like V1, doesn't really care about what the content of consciousness is. It's just faithfully representing whatever's hitting the retina without reference to what is in the mind. But now, as we move up to V4, third step in the visual processing hierarchy, we can see that a pretty dramatic difference occurs. So here, when we're looking at V4, we suddenly see that in the invisible situation shown in orange versus the visible situation shown in black, there's a big difference in the firing rate of the neurons. And some of these neurons shown on the right are showing a big increase in activity when the red circle is perceived as invisible. And some of them are showing a big decrease in activity when the red circle is perceived as invisible. And it doesn't really matter, increase or decrease. The big thing that we want to look at here is just that there's a large modulation going on. So let's think now about oscillations. So what we just saw is that spiking activity replicates previous studies. So this is a general finding then that V4 is conscious, shown by its modulation with the monkey's conscious perception, but V1 and V2 are not conscious. And that's exactly what Logothetis had shown in previous studies using binocular rivalry. You can check out my last video if you missed it to get some more details on that. But what about other modes of signal? So it turns out that spiking is not the only way that neurons can communicate with each other. They can also communicate via oscillations. Now fundamentally, the spiking activity of the neurons is really the only way that information can transfer from one neuron to another. But the probability of spiking and how well that spiking is listened to by a neuron's neighbor can be strongly influenced by the oscillatory state in which the neuron finds itself sending a signal. And by oscillatory state, I just mean the voltage of the surrounding tissue that the neuron is situated in. And that voltage can shift over time. And these are brain waves or oscillations because we talk about them being waves or oscillations because the shifting over time can be very regular. So sometimes we talk about alpha or theta or gamma or beta oscillations. Today we're going to be focusing on just alpha and gamma. So the alpha oscillation we'll talk about first is a 12 Hertz oscillation, give or take. and we're going to be looking at power changes in alpha in primary visual cortex. Now, the first thing right off the bat is this is a very different result from what we saw when we looked at spiking activity. So whereas with spiking activity, V1 did not modulate at all, now when we look at alpha power, shown on the y-axis, so this is just relative to a baseline 0, how much change in the power do we see in the alpha band, and we can see that there is, first of all, a quick spike and then an overall decrease in alpha power when the drifting dots come on, the dancing dots. But the drop is bigger for the invisible situation than for the visible situation. So this then seems to be some evidence that V1 is actually being modulated by consciousness, where when we looked at spiking activity, it was not. So now let's take a look and see what we see in V2. And V2, again, just as in V1, is showing modulation in the alpha band. And we can see that V1, I've just left it down here at the bottom. This is the finding from V1 is actually happening a little bit earlier than V2. So not only does this look like V1 is being modulated by consciousness, but V1 is actually leading the day here and being modulated by consciousness really early. So, and then if we move along and we take a look again further up the processing hierarchy, we can see in area V4, again, the same pattern where invisible trials, where the monkey fails to see the red circle, we see a decrease in alpha power, so a decrease in that slow 12 Hertz oscillation. And now if we just take a look at the timing in a little bit more detail, we can see that that timing seems to follow the generally feed-forward visual hierarchy, where V1 is first, V2 is second, and V4 is third. And specifically, V1 is showing modulation as early as 297 milliseconds, then V2 comes in at 428 milliseconds, and then V4 comes in at 455 milliseconds. So we can see a pretty big lag there between the modulation in V1 and then the modulation in those subsequent cortices. So let's interpret alpha for a second. So the V1 signal is first. That's the really big deal here. Not only is V1 being modulated, which is different from the spiking result, but V1 is first, so that's kind of crazy. So V1 consciousness leads to later areas. That might be one way to interpret these findings, is that V1 is actually the initial start of the conscious perception, and then that just feeds on forward as the conscious perception takes form through further processing. So the alpha decrease with invisible is kind of counterintuitive. So in some previous videos, we've talked about the alpha rhythm a little bit. Now keep in mind, here we're measuring the alpha rhythm from inside the head. That is a little bit different from measuring the alpha rhythm outside the head. But still, if we think about the general intuition of the alpha rhythm as being kind of a default state, a state of non-processing, especially associated with closing the eyes and not seeing any kind of visual stimulus, then it seems kind of strange that when something goes invisible, the alpha rhythm would drop. If the alpha rhythm is associated with a lack of visual processing, then something becoming invisible should be associated with an increase in alpha. So what's going on? It's a little bit weird, and it's something that I'm going to kind of loop back to in a little bit. But just keep that in mind, a little weirdness. So what about higher frequencies? So the alpha rhythm goes at about 12 Hertz, 12 cycles per second. What do we see if we take a look at some higher frequency or faster brainwaves? So let's take a look at gamma, which moves at about 40 cycles per second. And now we see something that looks a lot more like what we saw with the spiking activity. No change in V1. So whether something is visible, shown in the black line, or invisible, shown in the orange line, no difference. And then V2, same story, just like we saw with the spiking activity, no difference. And now V4, we can see a big modulation. So V4 has a big modulation with spiking activity and also with gamma. It seems like gamma changes somehow track the changes that we saw with the spiking activity, where V1 and V2 had no spike changes, they also had no gamma changes. Where V4 had spike changes, it also has gamma changes. And then if we take a look at the timing here, now down below I've put back here the modulation in area V1, that was our earliest one, remember, in the alpha band. And what you can see is that V4's change in gamma actually leads V1's change in alpha by quite a bit. So let's just go ahead and add that onto our list of timing here. V4 is having gamma modulation way back at 154 milliseconds after the dancing dots come onto the screen. So this is kind of a lot to unpack, but let's think about how do we interpret gamma for a second. So V4 signal is first. So it's not something that is flowing from V1 up through to V4. V4 has the conscious signal first. So the V4 signal could modulate earlier areas, and that might be what we're seeing when we look at that alpha signal coming in V1 and V2. So alpha changes might reflect V4 modulation. And V4 consciousness is choosing what it listens to. That might be one way that we interpret this change in gamma and the subsequent change in alpha. So what might this kind of generally mean? So conscious modulation of spiking does not occur until late processing. So that implies that there's no consciousness happening in V1 and V2, but consciousness starts to have an impact on processing when you get up to V4. So alpha modulation, though, is everywhere. So we do see changes in that low frequency band. Gamma modulation tracks with the spiking, tracks with the consciousness. So the gamma and the spiking changes happen early as 150 milliseconds. So from the time that those dancing dots come on the screen to the time that the monkey has a divergence in neural activity between the conscious and the non-conscious representation of the red circle is as early as 150 milliseconds. So that's super fast. So the alpha flows V1 up. That was something that we saw, that the alpha modulation actually starts in V1. So let's think about how this all might happen a little bit schematically. So first, there's a reflex arc initiated. Information hits V1 and then it just moves dumbly to V2 and then V4. This is the spiking activity that is not changing no matter what, happens super fast, faithful representation of information that hits the retina, goes to V1, goes on to V2, goes on to V4. Then conscious processing somehow begins or gets initiated in V4. We see this with the modulation in gamma and the modulation in spiking. Something goes on where some parts of the information that has gone through this reflex arc from V1 to V2 to V4, some part of that information gets taken up and made conscious, where other parts of that information are not taken up and remain non-conscious. So once that conscious perception begins to form, what happens next? So consciousness sends feedback to V1 to tune and select input, and this may be sent via the alpha rhythm. Specifically, the alpha rhythm could be inhibiting non-target info. So if we think about the alpha rhythm as kind of a default state, a state of non-processing, you could imagine a situation where the alpha rhythm inhibits all of the non-conscious stuff that's coming into V1. And in the situation where we have lots of dots shifting all over the place, the non-target portion of the screen is actually the majority. So this may be a situation where not processing that information or inhibiting that information actually requires more alpha in a situation where the red circle remains visible than when it goes invisible, and may go some distance to explaining the counterintuitive nature of more alpha associated with a visible red circle. And then that inhibition of non-target info continues up the processing stream, creating kind of a loop of tuning that allows stabilization in the conscious percept. So one thing to keep in mind here is that the recordings that are being done in very localized areas. The tip of the electrode wire is only in one spot, only listening to a very small population of activity. But the total area of V1, V2, V4 is really big. So when we look at this modulation in alpha, it's important to realize this may be something that's happening globally across the whole area and kind of depressing the activity of all of the surrounding stuff that is not the target red circle, allowing the red circle to be stably represented in consciousness. When this inhibition, as indexed by the alpha rhythm, fails, it is then that we see a decrease in alpha and a loss of the inhibition that was tuning the conscious perception, and then the red circle becomes invisible. So a lot of this is kind of a little bit out there. I can't really tell you for sure if this is really what's going on. It's a little bit of me making some leaps and some intuitions from the data that Logothetis and colleagues have provided us. But I'll leave you with a few remaining questions. So which component in this system is the experience? We've talked about modulation of activity by conscious processing, but where actually is the experience, the qualia of consciousness? And this is a thorny issue. What is the role of attention? So Logothetis notes in the discussion section of one of these papers that in binocular rivalry research, it's been shown that people have no ability to modulate which of the two stimuli being presented to the eyes is seen in consciousness. So if they can't modulate it with attention, then perhaps these changes are somewhat automatic. So there can be selection of information into consciousness automatically. But we also know that we can choose what we think about. How does the automatic selection of information into consciousness interact with the choice of what to bring into consciousness? And how do different states alter this content flow? So I showed you in an earlier video that DMT, the hallucinogenic drug, causes a dramatic change in the alpha rhythm, as measured by EEG. And we saw here that the alpha rhythm seems to play a key role in helping the brain tune its conscious input. What happens then to conscious input when the alpha rhythm is completely lost? Now, based on this study, we might expect that a loss of the alpha rhythm would lead to a loss of, in this case, the red circle. Some kind of loss of control or loss of tuning, loss of selection of the information coming in from the outside world. So anyway, those are the questions that I'll leave you with for today. A lot of stuff covered in this video, just overall take-home point. Early areas of visual processing do not seem to be conscious. Higher areas of visual processing do seem to be conscious. And those higher areas seem to feed back to the lower areas using slow wave brain waves, the alpha rhythm, in order to select and tune the input that they receive into consciousness, creating kind of a loop, a feedback loop where all areas of the brain are interacting with each other to kind of create that conscious experience represented in the higher visual cortices. Anyway, a lot of stuff to bite off. I've got a link to a blog post down below if you want to check this information out in text, kind of spend a bit more time chewing over it. Please click the like button if you liked the video, subscribe if you'd like to see some more, and you can support me on Patreon by clicking the link below. Awesome. Thanks. Have a great day.